say that 72 hours ago I couldn't speak. Not only that, 72 hours ago I was in Singapore and couldn't speak. So I landed at 10 o'clock or thereabouts yesterday morning. So I'm still just a little delicate around the edges. I hope that I will actually get to the end of this hour with a voice that still works. If not, I shall just start waving my hands. Okay, so we're going to talk about designing efficient SQL. Quick introduction. Yes, I'm an independent consultant. I like to make a big fuss about that thing. I've been using Oracle for more than 25 years now, more than 26 years I think it actually says. What I tend to do is very short-term stuff, just a couple of days here and there. Although if I do fly to Singapore, I do tell them I will stay there for at least a week. Because it takes 2 days to get there, or it uses up 2 days to get there. Briefings, troubleshooting, sanity checks, this sort of stuff which can be very focused and make a big difference in a very short period of time. It's the sort of thing I do. A few of the plaudits, pats on the head, odd little awards and things like that. The one I tend to make a big fuss about in America is this one. I have an O1 visa. That's the bit of paper which says I'm, and I quote, an alien of exceptional ability. Right? However, I'm not going to renew that this September, so from September 10th, I will just be an ordinary person of exceptional ability. And I won't, the O1 actually lets me earn money in America, which used to be quite nice. But interestingly, over about the last year and a half, the people who used to say, there's absolutely no way you can come into our systems over VPN, are now saying, do you think you could possibly come into our systems over VPN? Because, it's very expensive flying you out here, and the hotel bills and all the rest of it. And suddenly people want me to use the internet to get onto their systems. So I'm doing less work in America, less inclined to renew. Okay, the books I've contributed to, the books I actually wrote. So our topic is designing efficient SQL. We're basically going to pick up on 3 key points. The problem or the difficulty with making sure that your SQL is efficient is that you actually have to know what you're doing. Right? You have to know what the data looks like. And you can get kind of lucky, you can make guesses, but really when it comes down to it, the difficult stuff, you have to know in some significant detail what the data looks like. And when I say the data, I don't just mean what the rows are, what the columns are and all the rest of it. A little bit about, I suppose, the metadata, what the indexing is and how the data is distributed and so on and so on. Once you actually know the data and what you're trying to achieve as an extract, the query against that data, the next question is it actually in principle possible to produce an efficient execution path against this data? Could I actually stand here and say, well, if we got Oracle to pick up data from this table first using this index, and then go over to this table and get the related data using this method and then join it like this before we go over to the next table, can we actually invent something which sounds like a reasonable amount of work for getting the job done? And if you think it's possible, you can then engineer a query and throw it at the optimizer and say, well, can the optimizer find it? Because there are things which the human mind can come up with which currently the optimizer cannot actually do. And, well, occasionally you can re-engineer your code, you can do extreme things with your code to say, I will tell the optimizer exactly how to get through the various stages of what I want it to do, and I will force it into a path which normally could not possibly take place. So those are our basic 3 steps, but a huge fraction of it, in many, many cases that I see, simply revolves around the fact that I can go up to someone and say, well, look, how many orders does your average customer place? And they'll say, well, I don't know. Well, if you don't know how many orders a customer places, how can you possibly work out if there is an efficient way of running a query, select all the orders for a customer since the 1st of this month? If you don't know what your customer does, how can you know what a good execution path is? So knowing the data is an enormously important bit of actually getting the efficiency. And it falls into 2 pieces really, right? How much data? Give me some information about the volume of data, or the volume of data I expect this query to return. But volume is not the only consideration. almost on an equal footing with how much data. You need to know where is that data, how scattered is that data, right? And if you don't consider both of those, you can't actually take best advantage of engineering your SQL. Now, without going into pure technicalities of how does Oracle run a query like this, what does the data exactly look like in Oracle terms, looking at Oracle tables, Oracle objects, physical mechanisms that Oracle uses, take a look at those two informal queries and just think for a moment, how different are those queries from each other? Select all the orders placed by a given customer and select all the orders placed on a given date. I mean, textually, grammatically, linguistically, they look remarkably similar. But thinking in business terms, thinking in real-world activity, what's dramatically different about those two queries? A dramatic difference introduced basically by changing the word customer to date. And just to give a moment, pause for thought. Distribution. Where is the data? All the orders placed on a given date. Well, they all happen on the same dates. They all happen around the same time. They all appear at the same time, probably end up in roughly the same place as you insert them into the database. All the orders placed by a given customer, well, this guy placed an order 3 years ago, and another one 2 years and 10 months ago, and another one 2 years and 9 months ago. Then he didn't come back to us for another 6 months, and then there's a couple which he placed 2 years and 4 months ago. We could be talking about exactly the same number of orders, but one of those sets of orders appear in a very small part of the database. One of those sets of orders could be massively scattered across the entire database structure, the entire table. Oh dear, that doesn't bode well for the rest of this hour, does it? Okay, so all orders placed by customer, right? Big table, and scattered through time, we get the orders placed by customer. Right? That's our pattern, that's what we need to know. Orders placed on a given date, and I've said here, well, let's pretend it's yesterday. There's our orders. Same number of orders, completely different patterns of the data. And the patterning of the data can make a big difference to the way we choose to access that data. It might make sense, given the top pattern, to say, well, let's just do a brute force through the entire table as fast as we possibly can. Let's buy an Exadata for that one. Right, and just rip out the whole data set and pick out the rows we need as we go. Whereas for the pattern below, we might say, okay, I can see that there's actually quite a lot of data there. On the other hand, it's all in one place, so when we start getting at that data, we won't just pick up one row, we'll perhaps pick up 50 or 60 rows in the same block on the very first row we're after, and the cost of picking up the 49 extra rows will actually be a lot cheaper because we've picked up the first of the 50. And of course we've got another little aspect to this one. Right? I said, for example, yesterday, what's the difference between picking up all the orders placed yesterday and all the orders placed last Christmas? Because again, from a sort of business type perspective, last Christmas is very different from yesterday. And it makes a difference when you query the data. Sorry? Cash, exactly. What are the most interesting orders on your system? The ones probably placed in the last 4 or 5 days. They're in the cache because someone's placed them. They're in the cache still because someone's checked them. They're in the cache because someone's picked them. They're in the cache because someone's delivered them. They're in the cache because someone's invoiced them. The orders placed in the last, I don't know, the last week perhaps, are the orders most likely to stay in the cache for the duration because there are all these different business processes which keep going back and revisiting them. So when you look at this table, right, well, the orders placed yesterday perhaps are 100% cached. And so whilst the orders placed last Christmas are down here, and when you go and query them, you physically read them off disk, right? You might say, well, if I'm going to physically read that much space, well, yeah, then we'll fall back to the brute force table scan. You might say, well, this many orders, which are actually likely to be cached, will go to the index. Same number of orders, same clustering down there, but yeah, actually maybe because it's last Christmas, we'll actually just do the brute force approach. because we're going to be reading the disk anyway, so let's hammer through it. So knowing the business, knowing the data, knowing the practices that are going on makes a big difference to how you approach something which seems to say, find me 1,300 rows from the table. Okay? Are they scattered? Are they clustered? If they're clustered, are they clustered in row cached, or are they clustered but physically things we have to move across? And that's business information. You can discover it if you're the DBA by looking into the database, but it's business information that helps you make decisions. That's just a note summarising 3 points. And then of course you end up with the problem that if you know your data, you probably know your data much better than Oracle does. You've got all this extra information which is about the patterns in the data, the distribution, the caching of the data set, and Oracle has got this simple-minded little model which says, well, yeah, we've got 1,200 different days in the year, so any one day is 1,200 of the data. Right? We've got so much data for a particular customer. We have no idea what the caching looks like. We've got some sort of idea of the clustering of the data because we can look at an index and check clustering factors. But Oracle has a very simple-minded model of what your data looks like. And very often, when Oracle does what is obviously the wrong thing, it comes down to, well, Oracle thinks there's a lot more data than there really is, or Oracle thinks the data is extremely badly scattered across the whole table when you know it's very well clustered. Oh, and you also know it's going to be cached anyway, so even if it were a bit scattered, you'd still like to use an index because you can take advantage of it. So the biggest problem that I tend to see in terms of Oracle did the wrong thing is that Oracle's model isn't as well informed as our model, our understanding of the data. So knowing the data is extremely important. Now, on top of everything else, I mean, there are all sorts of reasons why Oracle gets it wrong. And very often the calculation of how much. I am not going to go into all the details of all these things here. It's just a brief hit list here. Correlated columns. Oracle thinks that any 2 bits of data in a row are completely independent of each other. So when Oracle says, what's your star sign, what's your date of birth, Oracle thinks your star sign and your date of birth have absolutely nothing to do with each other. Whereas in fact they're remarkably synchronized. Like, that type of behaviour, or perhaps let's make it slightly realistic, your DHL. Right? You want a report of all the parcels you picked up in the last 24 hours and have not yet delivered. Right? But from Oracle's perspective, there's no connection between parcels picked up in the last 24 hours and parcels not delivered. From a business perspective, which parcels have you probably not yet delivered? The ones you've just picked up. You know, you're almost asking the same question twice when you put those 2 predicates together. But Oracle thinks they're completely independent predicates. So correlated columns. Uneven data distributions. Oracle does give us histograms to try and deal with the status. 99% of the data is in status completed, and we keep asking queries for status new. Right? Unless we've got a histogram in place and code which can handle histograms, and that is something people often forget, Oracle's just basically going to say, you've got 2 possible values, it's a 50-50 split. So we run into all sorts of interesting problems. How many people earn more than the average salary for the company? How many people have got more than the average number of legs? No? Oracle thinks that 5% of the people have got more than the average number of legs. The right answer, by the way, and you may not believe this, is almost everybody has more than the average number of legs. Because a small number of people have either lost or not been born with both their legs. Therefore, the average number of legs for the human race is just slightly less than 2, which means the average. Oracle has no idea about the actual significance of things like averages. Very often, Oracle throws in a guess which says, "Don't know, call it 5%," or "Don't know, call it 1%." Oracle has a few magic numbers which appear when it has to guess. Interesting things happen with that type of stuff as well. Again, Oracle doesn't really know what's going on. We know better because we know the data. And bind variables are a major pain in the backside. But I'm not going to go into all the horrid possibilities that appear there. But there are plenty of reasons why Oracle gets the wrong estimate of just how much data before it worries about how is it scattered and where is it cached. Right? So, We need to know the data. It helps then if we also recognise why Oracle doesn't have as good a picture of the data as we do. Or it helps if we recognise that Oracle's come up with, oh, the estimate here is 5,000 and my estimate was 25,000. Oh, well, hang on, Oracle's just used a magic 5% here, that's why its figure's wrong. If we recognise the mistakes that Oracle makes, it's enormously helpful. So, if we've got that information, how do we proceed? Loosely speaking, you can think that there are two basic strategies for getting data out of the database. This is more simple-minded than it really is, but it's not a bad guideline. Are we going to pick a high precision mechanism? Something which essentially says, we think we're going to pick small amounts of data, relatively small amounts of data, right? There is no absolute number where you can say that's small and that's big, of course, but relatively small amounts of data. We will do it because we have the right indexes that we can use to access the data. We will use nested loops. Because we're going to do something high precision, we may do it 20 times, 40 times, 100 times. Every time it's a small operation, it's high precision. So there's a high precision type of strategy, and there's the brute force type of strategy, which essentially comes down to, in most cases, we'll do table scans, or perhaps a very large index range scan. It will take a large volume of data and then do brute force hash joins with it. And of course, in many ways, we tend to see the first one for OLTP systems until you get the overnight batch updates or the overnight big reports. The brute force stuff tends to be the data warehouse, the decision support things, or the cases where you're creating your materialized views overnight, ready for the OLTP system to be redirected if it starts running reports. So we've got those two types of choices. When you're thinking about your data, it's relatively easy to think, well, yes, this is small, we should think nested loops. This is big, we should think hash joins, table scans. And then you start worrying about why Oracle does something amazingly stupid by taking a brute force approach when you know that the answer should be a high precision thing. So a point I like to make people is that the sort of psychology of how this works. I think everyone's happy to recognise the idea that, well, some things are obviously small high precision, some things are obviously big bulk brute force. Okay? So we can look at a sort of spectrum of work. There's the high precision nested loop end of the workload, there's the massive brute force end of the workload. And of course, we have all sorts of varying requirements for queries. We cover all sorts of possibilities from the very tiny high precision to the massive brute force. So we can imagine this sort of spectrum as a line which spreads from our two extremes, and consequently, it's a continuous line, there has to be a point somewhere, and let's pretend it's in the middle for the moment, there has to be a point somewhere where you could say, well, with this particular query, it doesn't matter whether we take the high precision approach or the brute force approach, right? It's one of those sort of intermediate grey area queries which says, whatever you do, it's going to be fairly expensive. And there's a break point which says, well, yeah, Oracle might switch between nested loop and hash joins, but it won't really make any difference. The performance is going to be about the same. And just from accepting that you recognise that there are two extreme cases where the approach, the obvious approach, the correct approach is obvious, implicitly there have got to be queries where there's this break point and one extra row either way shouldn't make any difference. The switch shouldn't make any difference. But of course what actually happens, people come up with this notional breakpoint, and the optimizer, because of its guesses, because of its ignorance about caching and so forth, can say, well, you see, I think the breakpoint's down here. If my estimate of cardinality or clustering is going to put me about here, just slightly less, and at this point over here, I'll do a nested loop. And if I have just slightly more, for this entire range, I'll do a brute force hash join. And this is the point where you're saying, well, I'm here. Why is Oracle doing a hash join? It's a small query. It should be done with the nested loop then. And all it is Oracle's arithmetic went wrong. Oracle's estimate said it's a pretty small query, and the breakpoint is down at the small end. It's just made a mistake in its estimate. And of course, the opposite happens up here. Oracle's come up with the arithmetic and says, well, the breakpoint between nested loop and hash join is about this many rows. And so you're requesting a large volume. You know it's a large volume. You know it's hard work. And Oracle says, well, from here down to there, it's nested loop. This is small. Left-hand side there, small. It's easy for Oracle to get the wrong arithmetic and do the wrong thing. And you can see it switch to do something insanely stupid as a consequence. And the question, of course, is how much data does it actually take to persuade Oracle to do something insanely stupid? I mean, how many times do you see people saying, nothing has changed and the performance is now dire? Right? Yesterday it was great, today nothing changed. Rubbish. I bet you some end users put some data into the database in the last 24 hours. Something changed. Of course, people putting data in doesn't really make a difference. But if you collect statistics and Oracle finds out that people have put data in, that makes a difference, potentially. How much change do you have to have before you have a catastrophe? Well, I've just said, you can imagine there's this hypothetical breakpoint where it doesn't matter whether you do a nested loop or a hash join, the performance will be so close either way, you won't notice the plan has changed. And all it takes is one row. One row either side that Oracle knows about is sufficient for Oracle to say, on the breakpoint, one row less, it's nested loops. One row more, it's hash joins. And you won't tell the difference. Or you wouldn't if Oracle were perfect. The optimizer was fantastic. But the previous slide says Oracle didn't put that in the right place. They put it in the wrong place. And when you put your one extra row in, Oracle says, well, it was small, but now it's big. You're still sitting there thinking, it's small. It's 13 rows instead of 12. Now, why is Oracle taking 3 hours to run this query? One row. Did anything change? Yes, the end users keep using the damn database. And occasionally Oracle gathers stats. Or occasionally, the gather stats which you do every single night creates a histogram where the histogram boundaries just shift slightly. Histograms are horrendous for stability. Right? Oracle tends to take small samples for histograms, and unless it's a frequency histogram and you get terribly lucky and do it at the right time, it's very easy for a histogram just to shift slightly, with Oracle to say, well, the data barely changed, but the histogram looks completely different. And this type of thing happens. You have to know the data, and you have to understand that Oracle does make mistakes and what those mistakes are. So let's look at data. In fact, first off, let's look at metadata. One of my favourite things to do when I get called in on the site where, generally speaking, people say, performance is just not good. There's no specific thing we would like you to fix, but the whole thing is not good. I mean, just browsing around, looking for resource consumption is an important thing to do. Where's the work disappearing to? What's taking up the resources? If no one will tell you what is wrong, what needs to be fixed, just looking for things that use up resources is quite helpful. But another thing that's really quite useful is how many indexes do you have that you shouldn't have? How many indexes have you got which are really bad indexes which aren't helpful at all? Right? Because they automatically take up resources. So a simple query like this, there's a much better one actually on my blog which brings out all sorts of things like the function-based index definitions, the uniqueness of the indexes, the constraints on the columns and so forth, okay? But a trivial starting point, deviate in columns, we'll have the table owner, the table name, the index name, and the column name, sorting here by the table owner, the table name, the index name, column position, right? Just showing you all the definitions of all the indexes. A little example I went to on one site, the biggest table they had, I thought, well, let's just look at the indexing on this particular table, so I just selected the table. They had a good naming convention. You know, they had first two letters, it was a short code to the table. They had FK if it was an index created to avoid foreign key locking. They had PK, there's one here, yeah, PK is the primary key index. They had UK if it was a unique index, there aren't any in this particular case, and so on. UD, there's a user-defined column in that. It's actually an index on trunk of update date. My query here, of course, wouldn't spot that, but a more sophisticated one would. Okay, so there were the indexes. Well, this was the biggest table on the system. Generically, inverse system was too slow. Too much work being done. Okay, OLTP type of system. Single biggest, most interesting, most important table. So let's run down the list. Group, foreign key, group ID. Next index down, starts with group ID, second column's role ID. Well, that foreign key index is a waste of space because the next index down protects the foreign key. But they didn't know that. Every time they declared a foreign key, they created a new index for it. They did not check that they were already covered. In principle, you could just drop that index. In practice, there might actually be some queries that change execution plan because of things like clustering factor. That's the most likely thing. Leaf block counts, possible but less likely. Okay, so that could be dropped. We'd have to check a little bit. We might have to write some code which says this is what we want the statistics for that second index to look like. Carry on down the list. We've got the org ID here, and we've got the org FK. Those two indexes start the same way. That foreign key index is also redundant. Keep on going. We've got the person foreign key index, but here we've got the person for ID followed by the primary key of the table, so there's a third index, which is redundant. We've got a foreign key index here on role. There is no other index that starts the same way. So as far as foreign key locking is concerned, that index is not redundant. There are 32 roles or something like that in this particular table. No one is going to modify a role. No one is going to delete a role from this table. That is probably not needed. You do not need to create a foreign key index if you're not going to delete or modify the primary key. Right? That's almost certainly not needed. However, it's a very cautious organisation, dare I say government. Right? A very cautious organisation can't drop that index. However, role is very repetitive. So, given that the role is very repetitive, we don't want to repeat the value once for each index entry. Let's repeat the value once per leaf block. And that will nearly, in this case, halve the size of the index. So let's compress this index because role is very repetitive. And in fact, when we do that, we can go back to the rest of them. The group ID is very repetitive, and the group combined with the role are actually very, very repetitive. Right? So we could actually compress this non-unique index on both columns, just say compress. This index here, the org ID, is very repetitive. That's the primary key of the table, mind you, so the index is actually technically a unique index. We will just compress on the org ID, compress on the first column. And down here, person ID, same thing. The person ID is reasonably repetitive, so on average 9 or 10 times a person appears, maybe gets up as many as 20, a few people appear 100,000 times, right? But the person ID is at least a little bit repetitive, compress one. And then we come down to this one, the trunk of update date. Well, they update about 30,000 rows per day, so this is very repetitive. So that could be compressed. However, before we compress it, let's just ask the question, what do we have this index for? Why do we want to get relatively efficient access to all the rows updated on a given date? Who actually reads the report of 30,000 rows of data, which are the 30,000 rows updated yesterday? No one. Why is the index there? Don't know, just in case. And bear in mind, of course, update date, not creation date. Creation date would put all the rows in the same place. Update date could be rows scattered across the last 3 years which have been updated. So this index, when it hits its 30,000 rows for a given date, could do a huge amount of work randomly throughout the entire table. It's probably a query where you could say, select one column, one other column from this table for a given chunk of update date, and Oracle wouldn't use the index. It's a total waste of space. It should be dropped. On top of that, trunk of update date. Now. We delete a row back there, we insert it up here in the index. And we all insert at the same place at the same time because trunk of update date is now. Well, the start of today. We've got a concurrency threat on that particular index. We could have loads of rows being inserted into the same place in that index at the same time. We might get buffer busy waits. There is a catastrophe that happens with concurrency on index inserts. If you do a search on my website for the word explosion, right, Oracle says they've fixed this bug. They have not fixed this bug. I re-emulated it in Oracle 12.1 a couple of days ago. What happens is that the index leaf blocks end up being 50% ITL entries, interested transaction list entries. Half the block disappears on something which can never be used ever again. And then with the concurrency thing on top of that, I mean that's the concurrency bug. On top of that, you tend to find that the block is constantly under 50-50 block splits, so the index is 4 times the size it should be. Oh, and bear in mind, we delete entries from the past, we bring them into the present. So there's this sort of historic tail end of the index, which has been emptied out because you've updated the rows and brought them forward. So that bit of the index over here is full of empty space. It's a catastrophic index, it's a rubbish index, but that's lucky because no one's going to use it. Except for the fact that they go over here, read a block, delete a row, come over here, collide with everyone else, inserting a row. Right? It's wasting a horrid amount of resources. So, shouldn't really be there. Damage limitation, we're going to drop it and rebuild it. I mean, ideally we'll drop it and forget it, but we'll drop it and rebuild it. And then regularly we will coalesce it in order to try and close up some of the empty space and clear up some of the mess. And we will build it compressed. Kind of helps, but it's a really disaster index. Just shouldn't be there. So, sort of 10 minutes looking at this index set of definitions, and I've said, yeah, we can drop half your indexes, we can compress half the indexes, and ideally we'd like to get rid of one of these things, which is disaster. So 10 minutes, just by looking at the index definitions. And then the 6 months of paperwork. Okay. That's metadata, right? Just check that you aren't wasting resources. It can be difficult to get rid of indexes. There's always a certain fear, there's always a certain oddity that Oracle misbehaves, but it's at least worth knowing that you've got the redundant indexes or you've got the indexes that can be compressed. Okay, knowing the data. Very simple thing here. If you've got a column with what you think are just a small number of distinct values, just a quick check, state, count, star, group by. Something as easy as that might show you data that looks like this. And when you look at that, you can come up with all sorts of ideas about what you might do. For example, if people are only interested in these rather rare values, well, you've got an index which is much bigger than it needs to be because it's got loads of that garbage in place. So what might you do? You might create a function-based index. You'd have to change the code, of course, slightly. Function-based index which conceals that, so you end up with a very small index. That's a nice idea. 11G, of course, you'd go for the virtual column. Virtual column, you might not even have to change the code to find that an index on the virtual column behaves really nicely for you and is very small. You might say, well, I've got to live with what I've got, but I will definitely create a histogram, frequency histogram, which tells us about that distribution. Right? Other things you might do, well, in some cases, you might play games and say, well, let's do list partitioning. Let's create a list partition table which says that goes into one partition, the rest of it goes into another partition. So when you update the row, it stays in the interesting partition until it hits completed. It costs more, of course, to do this, but it then moves to the boring partition. Right? Oh, clever things you can play here, because you can create an index on the partition table, which is a local index, right? And mark the boring bit unusable. And the 11G says it's unusable, it takes no space. Oh, and if you query this thing, I'll do an index access path into the main data set and a table span into this other partition. Right? Not that you'd write the query that would do that, but that's what you can do. Looking at the data could give you ideas about making your options more efficient. Of course, sometimes you don't get useful results back. It's a big table perhaps, and there's quite a lot of values for the column in question. If it's a very big table, you might start just by doing a sample. Very small samples actually, rather than 5%. Sample 5% of rows, 5% of the blocks. 5% of the blocks don't use 2 consecutive blocks every time. And here there's a seed number, so your sample is always the same sample each time you run the query. These are slightly newer versions of the sample command here. In fact, I'm not sure that one's documented. Okay, you do that and you find, oh dear, bad news. I've got 10,000 distinct values for column X. Not a useful report. Well, not as it stands. But have a look. 2 and 3 both appear 12 times. 6 appears 9 times. A load of values here appear just once. it would be nice to have some information which says, well, how many different values appear 12 times? How many different values appear just once? Right? But we can take this query and put it into an inline view. Value, counter star, let's count these things. Count frequency. Put it into an inline view, aggregate on that count, and see what we get. Now 10,000 lines changes into 22 lines. Thousands of values appear just once. Worst case scenario, there's a value which appears 22 times. The 12s, what was it? How many values appear 12 times? Here we go, 99 values appear 12 times. Or if we had to optimize a query against this table, a query where column X equals constant, looking at this, we could say, well, if we optimize on the assumption that we will return 10, I think it's, no, maybe 11. Let's optimize on the basis that we expect 11 rows. That's a good representative approach to this particular table. Of course, in other tables, we might find everything has a relatively small number. Oh, except I've got 5 values where suddenly it says, yeah, we've got 5 values where you return about 2,500 rows. You look at that and think, I've got to come up with a strategy which says if it's one of those 5 values, I do one thing, anything else, I do another. But if you don't know you've got those 5 values, how can you optimize your query? We can go a bit further. Rather than counting how many rows, bear in mind, I started off saying it's how much data you've got and where is that data. Let's not count column X for each value. Let's not count the number of rows, but count the number of distinct substrings of the first 15 letters of the row ID. The first 15 characters of the row ID is the object ID, file ID, block ID. Right? So this says for any one value, counts the number of different blocks where you can find it. And that's the other important part of knowing your data. How many different blocks will you have to visit to pick up your data? Same thing applies then, having done the count like that, turn the thing inside out. We've got something here which says, I've got 9,000 values where I'll only have to visit one block. In my worst case, I've got a couple of values where I'll actually have to visit 19 blocks. And we may have had some values which had 2,500 rows to pick up, but maybe when we do this, we find that we don't have any values where we have to go to more than 10 blocks. Maybe those extreme values, the 2,500 rows, are just packed really well into just 10 blocks. So two slightly different queries, same pattern, two slightly different queries. We've got how much data should you expect typically, and how many blocks should we expect to visit typically, which is enormously useful in understanding the data when we start querying it. I've got a couple more here. I'm not going to talk through them in great detail, but we can play games as well with indexes. This is just cut and pasted from the from doing a trace file of DBMS stats, gather index stats. Okay, that type of query appears. This pair of columns is the index definition that Oracle was using. That's the object ID of the index. There's a couple of funny, interesting internal functions being used by Oracle when it gathers stats on indexes. What I'm going to pick up is this sysop LBID, because this is the leaf block ID for which contains the row ID for this row in the table. Right? Now, if you go to this location, I think it's still there. APRES put up chapter 5 of my book on cost-based optimized, the clustering factor chapter at this location. Loads of stuff about this at that particular site. Sysop LBID. Find me the leaf block ID for each row in the table and count how many times each leaf block ID appears. In other words, for each leaf block in the index, how many table rows are identified by that leaf block? Right? How effective is the index? Again, we turn this inside out. Right? How many leaf blocks identify 100 rows in the table? How many leaf blocks identify 400 rows in the table? How many leaf blocks identify 10 rows in the table? If you're worried about an index, why is my query inefficient when I seem to be using a good index
then maybe you want to look at how healthy that index actually is. Maybe you need to know something about how Oracle's handling that index. Now, a typical B-tree index with randomly arriving values will give you this type of picture when you run that query. Again, there's stuff about this on my blog. This is an index on a key. The key value was 200 bytes roughly. Okay, you can see here how many blocks have got 17 keys in them. How many blocks have got 40 keys in them. 40 is the highest here. The key value is about 200 bytes long. The pattern we get here, small numbers up here at the extreme lows, small numbers up here at the extreme highs, sort of bulge here roughly in the middle. These are the leaf blocks which are just coming full. Right? The next time I get to one of these leaf blocks and insert an index entry, it will split in two. We'll get two leaf blocks down here. Right? That's the leaf blocks which have just recently split, and as time passes they will slowly fill up, and roughly here at about 70% utilization, this is where the bulk tends to be. You get this sort of bell curve type pattern. Right? That's your typical average, healthy, random arrival B-tree index. Have a look at some of your indexes if you think this query should be efficient, and yet this index is doing an awful lot of work. Right? Gives you some idea of the picture. There's different ways you can analyze indexes. This, by the way, is chunk of update date, or half a dozen pathological ways in which indexes can collapse. Okay. This is actually an index which I use as a FIFO queue, first in, first out. We insert rows on a sequence number that's continually increasing. We delete rows in the past, but we don't actually delete all of them because a few of them just get left behind by accident. Right? So we've got a few blocks which are the high value blocks, which have got 300 odd entries in them. We've got hundreds of leaf blocks up here where we've deleted almost everything. We've got an index which is enormous. The volume of data it holds is really quite small, and that volume is almost all in the last three blocks. Right? You do get some pathologically bizarre indexes. It's worth knowing about them. When you see that pattern, you have to ask the question, why? Why is it happening? And follow that up with, what are we going to do about it? How much work do we have to do to stop something slow and nasty happening? Maybe it just doesn't matter. Maybe the way we write our code, we only ever look at those blocks, and this, whilst it's a mess, isn't something we actually do any work with. Okay, that's 45 minutes on knowing your data. Now we can talk about writing your SQL. That, by the way, is probably about the right sort of way of thinking about it. You can't get anywhere if you don't know your data. Well, you can get lucky, okay? Yeah, people get lucky most of the time, actually. Well, no, Oracle gets lucky most of the time. Okay, so if the query gets complicated, draw the picture. That's it. Fill in a few extra details, of course. But if the query gets complicated, it's a really good idea to draw the query. Very simple query, really. Absolute hell to try and present this and information about something like this sensibly on screen because there's not enough space. 5-table query, 3-table subquery. Okay? How are we going to optimize this query? Well, what's it doing? We can see here 5-table join, customers, London, order date placed is the last few days, supplier location is leads and exists, and we've got down here suppliers not equal to leads again, suppliers product matches. If you read through that query, and it's been written to be as readable as possible, right? To make it look as sensible and easy to understand as possible. It's just a convention I happen to have. Different conventions will find, and you'll find that it doesn't match the way you think, and it looks difficult. But it's written to be easy as the way I write these things. It's just a query which says, I want orders placed in the last week where the customer was in London and the supply came from Leeds, and we could have found an equivalent product which did not come from Leeds. Okay, that's the sort of business statement of intent. That's an SQL statement which finds it. Okay, so how do we draw the query? Now, if you can't immediately think of the execution plan you expect, sketch it out. Okay, so a customer places many orders. That's the one-to-many crow's feet type picture. An order consists of many order lines, one-to-many. An order line is for a product. A product appears on many order lines. A supplier supplies many products, and I've got this one-to-many here in my subquery. A product could have many product matches, and a product match references another product, which references another supplier, or a supplier. So that's a picture of my query. I put a dotted box around here to capture the idea that this is a subquery in some way. That's my image. Now when I've got that image, I can start filling in extra bits of information. No space on screen, so I'm going to have to spread this over several screens, okay? Spread it over screens. Recent, I've got my sysdate, sysdate minus 7 to sysdate. That's one of my predicates. Other predicates. So I've got customers coming from London, I've got suppliers in Leeds, I've got an existence there for my subquery link, I've got my suppliers not from Leeds there. So I can fill in information about my predicates. It might be sufficient at this point to allow me to work out what to do next and write my query, but perhaps not. I need to know about indexes. Well, we've got loads of indexes which are my primary keys and foreign keys, okay? So it's an index which allows me to get from customers to orders. It's the foreign key index, so it's the direction of travel if I want to come in to orders, okay? I can write down some details about that index, about how effective it might be, okay? I've got other indexes in place. I happen to have an index on the date, so I could use an index to get in on my last 7 days of orders. I've got indexes about location there for customers and suppliers. Right? Fill in the indexes you've got, which may be helpful. Fill in the details about those indexes. Pick up all the numbers about the data. I'm just going to focus really on the orders table to give you the flavour of what we're going to pick up here. Orders, of course, was connected to two other tables, so there'll be a little fringe data around the edges. Without getting too detailed, order lines is the biggest table, far more rows than anything else, okay? So I've just got it here huge. Actually, I put in some real numbers if I was doing this in great detail. Orders is a big table, okay? You know, one order turns into many order lines, and relatively speaking, customers is the small table. But I want some fairly detailed information about those tables, okay? Orders. I know I've got this index coming into orders, which is on the date. What does that do for me? What can I say about that index and its access path into the data? Well, I can do a quick check and say, well, yes, that index on any one date identifies 2,500 orders. Right? What else can I say? Oh, order dates, they all appear at the same time. That's an index where the clustering is good. That index will have a good clustering factor. I don't get very formal when I'm thinking about the indexes. I just tend to think of good clustering, bad clustering, totally catastrophic. Right? The number itself doesn't really help anyone. Right? So I just think about whether it's likely to be helpful. What else might I say? Well, actually, for recent data, using that index to go into the data, I'm likely to find that recent orders are very well cached. And that could be a very, very important aspect of the problem. Of course, I've got other indexes. I had the index going up into order lines. So what can I say about that one? Well, in this system, every order has about 10 order lines. In this system, well, order lines go in when the order goes in. The clustering is very good as I move from orders to order lines. I've got an index into the orders table coming from customers. What can I say about that index? Well, what about volume? I look through the data. Customers are extremely random in terms of their behaviour. Some of my customers have placed only 10 orders over the last 3 years. Some of my customers have placed an average of an order per week. So there's high variability in terms of number of orders per customer. And then clustering. Right? The clustering is very bad. I mean, a customer's orders are scattered effectively uniformly, let's say random, or let's say uniform, across the entire table. So coming into orders for a customer, well, the number of rows we pick up in the worst case isn't bad, but if we had to do it for lots of customers, it's going to scale up into rather expensive, because we're going to visit a very large amount of the table. Oh, we'll visit a large amount of the table, and then we'll throw away everything except the last 7 days. That's the sort of thought we should be going through as we examine the possibilities here. So we draw our picture. And then, with the information we've collected, we can start picking a path. we can imagine a path through the map, right? We just look at it and say, well, okay, what happens if we start with this table? Can I get to this table fairly efficiently? Do I get a fairly small amount of data from this table? If I've started here and I've got this table, where's a good place to go next? Can I do that efficiently? Should I do it with an index? Should I do it with a scan? Should I do a hash join? What? Where do I go next? If I go there next, can I throw data away, or do I find my data volume explodes? Do I get there very efficiently, or do I have to do a lot of physical I/O to get there? Right? And just literally, we go through and say, time after time after time, what could I do next? And there's this sort of sound bite, if you like, I come up with, which is start small, stay small. Right? Pick a place where you can pick up fairly efficiently, because it's a starting point, it doesn't have to be brilliantly efficient, fairly efficiently, a smallish amount of data. And then as you move through the subsequent tables, a large part of your aim is to say, can I keep my intermediate result small? Can I keep doing something which is as efficient? Avoids doing a large amount of work, a large amount of random I/O, avoids making that data set grow. Interestingly, a little example I've got on one of my presentations was an OCM query where someone said, this query doesn't actually do very much, or it shouldn't be doing very much, but it takes 29 CPU seconds to run. Checking through the execution plan, it got to the point which said, I've got 15,000 rows in this table, 15,000 rows in this table. When I join them, I'm up to 7 million. And the very next thing I do is a sort group by, which brings me down to 450. Right? In 28 seconds, was exploding the data to the largest possible size and then shrinking it down again. Right? The solution, which I left as an exercise for the reader, was why don't you take these two tables and shrink them down first and then join them? Right? Run time is less than a second. It was a difficult query. I mean, I couldn't understand it after I'd written it, right? But keep it small, don't grow if you can avoid it. Right? His problems, he grew, and then. Okay, so what do we do with this one? I think I'm actually going to stop after I've gone through this one and not do the next one. Just leave it as a general principle. Okay, there's our picture. You could say, well, okay, what happens if we start with suppliers? Let's go for suppliers and leads. Right? If we go for suppliers and leads, I'm picking that one because, we don't actually have many suppliers and leads, so that's a good place to start small. Okay, suppliers and leads, well, luckily that doesn't give us all that many products because we don't have many suppliers and they don't give us many products. So we're still quite small. We're going to go a bit randomly through the products table because a supplier says, oh, here's another product we could give you if you like. So a bit random going to products. But that's still quite small. What do we do next? Well, we could go this way or that way. Well, if we go up to the order lines, suddenly we're saying, well, scattered widely through the entire huge order lines table, we have some products. So that's going to be a bit like hardware. So let's not do that just yet. Let's go over this way. We don't have a huge number of products, so let's try and get rid of some, find matches which don't come from leads. That's clearly going to be a better strategy at this point. But having done that, what do we do? For each product that still survives, we're going to have a random scatter through the order lines table. So this is going to appear and it's going to be expensive. So we'll put that thought to one side. We won't start with the suppliers at present because actually we see there's a problem if we do. Where else might we start? Well, if we start with the orders table, last 7 days, okay? Last 7 days, well that's 2,500 orders per day. Last 7 days is 17,500 orders. That's quite a large number if I'm trying to start small. On the other hand, it's an order processing system. Those orders are in a fairly well compacted space, and those are the orders which are likely to be very well cached, so we're not going to do very much in I/O. So coming in here might actually be really quite effective. Right? So let's start with the orders. What do we do next? Well, if we go upwards, we're going to grow the data set. That might be efficient in terms of the order lines being well clustered and well cached, but actually, if we're only after London, why don't we throw stuff away as fast as we can? So we come down to customers. to throw stuff away, and throw that away as rapidly as possible. And then we can go up to order lines. And of course, as with products, when we go up to order lines, we expand the volume of data. But the big difference, of course, is that the data we're going to pick up is the data which is the last 7 days of data up here. It's the data which are likely to be cached. It's data which is very well clustered. So going up from orders to order lines is probably pretty effective. We're not exploding the data dramatically. We're not doing a huge amount of extremely random I/O to get to it. So we'll go up and pick up the order lines. And of course, once we've picked up the order lines, the only thing we can do next is come down and say, well, tell me about the product. And then once we've got to the product, we've got this question, well, for every line I've got here, and there may be a few thousand of them, should I go for checks to see whether there's something that doesn't come from leads, or should I go down here to find the things that do come from leads? Oh, well, you know what? I know that not much stuff comes from leads in our system. So we'll go down this way, because if I go from here to let's find the stuff that came from leads, we're going to throw away most of the data. So our next step is to come down, which gives us the smallest data set to run through this 3-table subquery. Okay? And that's probably the best path through that map that we could do. We get it by knowing what the data sizes are, knowing what the data distributions are, knowing what the caching type patterns are, and so on. We've got a picture, we've got a map, we've got the index definitions built in. All the information we need can be drawn onto that map. Now obviously, big sheet of paper, small writing. Oh, unless you know the data so well that you don't need to write every detail down. Very often just a sketch of what you're trying to achieve is enough to point you in the right direction, to show you the sort of strategy you need. Right? Draw the picture, walk through the map. Start small, stay small. If the query is going very inefficiently, is it because I've allowed the data to explode, I've allowed a random I/O to come into play, or a brute force approach, then really I should have gone off to some other table first to keep the data set small, to keep the query efficient. Right? Draw the picture, fill in the details, then try and find a way to walk through the map. Almost always, that will give you a straight, simple, straightforward execution path, which you can then write as an SQL statement, and if necessary, put in a set of hints to Oracle saying, this is the order in which you visit the tables, do not unnest this subquery, do not merge this in line view, use these indexes. Do a nested loop, do a hash turn. Hinting, high precision carefully, completely, is actually difficult though. So the thing I do say to people is, put in your hints to get the plan right, but bear in mind you probably haven't done it right. You've been a bit lucky. You put in enough hints that Oracle said, well, there aren't many options left, and it just so happens that the one I would pick is the one you wanted. But I've still got another 3,000 possibilities here, which I will spring on you one day when you're not looking. Right? So you put in the hints, which gives you the path. You've got to do this. You put in the hints, which gives you the path you want. When you've found that path, or with Oracle 11G, you can say to Oracle, that's the query, pull the baseline out of memory, store a baseline for this. Right? Don't just rely on your hints because you probably haven't done it quite right. Turning your set of hints into a baseline is a safer bet. Alternatively, if you don't want to use baselines, put in your set of hints, have a look at what the baseline would be, and you'll discover there's probably another 9 or 10 hints which you should actually have included. Right? It gets messy and bloody if you try and copy baselines exactly, because there's all these query block name things that outline leaf names. But at least the baseline thing will show you that there's more hints that you should have considered. Okay. So that's the strategy. To start, you've got to know data, then draw the picture. If it's complicated, draw the picture, because it's so much easier with a picture in front of you. 2 URLs there. Both of these are just about this particular query, this resulting picture. One of them is an SQL Server article I wrote. Okay, the method's the same, doesn't matter which relational system you use. One's an article I wrote for, Redgate actually, in one of their various guises. The other one is a presentation I did with Carl Haley from Embarcadero, because they produced a tool, largely driven by his efforts. They produced a tool which said, give me the query, and I'll draw this picture, and I'll fill in all the numbers about what happens as you join different tables together, and I'll give you an idea. I forget what they call this tool now, the visual SQL tuning. I'll give you an idea of the good path across these tables. Okay, at that point I'm going to stop and let you read these.